We've got a person who weighs 500 newtons is standing on a scale in an elevator. And remember, if they weigh 900 newtons, that is their force of gravity. The elevator is identical in all cases, and the velocity and acceleration of the elevators at the instant shown are given. List the cases where the scale is reading greater than 500 newtons. So we want to know, when is the scale displaying a value that is greater than their weight? Okay, so I want you to unmute, and as you see it, throw out letters. Just yell letters at me and tell me which ones.
B.
You got to unmute. Say it again.
E.
F, B,
F.
H.
F.
All right, so pause real quick. I'm asking for when the scale is going to read greater than 500 newtons.
H is the same as 500.
Yeah, I don't want to know the same. I want greater than 500. When is that going to be?
B and F.
E.
ECA.
Okay, let's pause for a second and let's talk about this. What did we say a scale measures? Is it your force of gravity or is it something else?
It's the normal
It measures your normal force.
Your
Based
normal
on-
force, right?
Oh,
Now,
right.
so if you're at a standstill, you're not moving, just like you're in your bathroom checking to see if your diet's working or your exercise routine, you know, you're feeling hyped up. You're 15 pounds that well, for me, 15 pounds like you gained over COVID, you're like trying to get rid of it, trying to make a joke. So smile, come on, it's not that bad. It's an ugly day outside, but hey, we're in class. So if you're just chill and you're not moving, you stand on a scale, your normal force up is equal to your force of gravity down. So your scale reads your normal force, but it's equal to your force of gravity. So the scale gives you a proper reading, right? Now, if you're in an elevator, if the normal force were to go up, that would mean that the scale reads something bigger than, in this case, bigger than 500 newtons, right? So what circumstance would the normal force be greater than the force of gravity? What would happen to the person in the elevator if the normal force went up and was higher than the force of gravity?
Then they would float. Or
They
Well,
would
they would go
upwards.
upwards,
they
right?
would go up. Yeah.
You would accelerate upwards because the normal force is pushing up on you more than gravity is pulling down. So you would not only just go up, but you would accelerate upwards, right? Because an imbalance of forces doesn't just mean you're moving, but you're accelerating that position. So your velocity is getting bigger and bigger and bigger every second. So if we look across these, to find a place where the scale reads more than 500 newtons, we're looking for a place that we are accelerating upwards. So that would be an A, like alpha, D, like David, E, like echo. Even though they're going down, it doesn't matter. Their acceleration is up. So there's three, A, D, and E, like alpha, delta, and echo, just in case my letter pronunciation is not that great. When would the scale read the exact same thing as 500 newtons? Now, tell me those letters. Exact same thing as 500 newtons.
C and G.
C and G, because there is no acceleration, right? If there's no acceleration, that means my forces are balanced. I have a constant velocity, balanced forces, it's going to read the same. Now, process of elimination, so I'm not going to like give you credit for answering this one, but when would the scale say something less than 500? That means that my force of gravity is greater than my force normal. Now, my force of gravity doesn't change. Therefore, it's my force normal that's reduced that allows me to accelerate down. The earth didn't pull on me harder for me to go down at an acceleration. My force normal had to be reduced to allow me to accelerate down. In that case, that would be B, because we have a downward acceleration. Also F and H. So B like Bravo, F like Foxtrot, and H like Hotel. If you have a downward acceleration, force of gravity did not change. Our mass is still, in this case, 50 kilograms. Acceleration of gravity is still 10 meters per second squared downward. But in order to accelerate down, the force normal had to change. Force normal can change. Force of gravity does not change. Does that make sense how I'm explaining it? Are we okay? You got a nod or thumbs up or something? Okay, okay, I got a response from like 2 people. That's awesome. All right, so that's, let's look at the second warm up. It gives us, we're like -1 minute in order to get this one done. So these scales, this says these graphs are of net force versus acceleration for 4 different objects. We want to rank the mass of the objects. So what I want you to do is I want you to look across the graphs and tell me which graph has the greatest object with the greatest mass. Which one has the greatest mass?
D.
I have a vote for D. Anybody else?
C. C.
C.
I think it's C.
I think it's C.
C.
All right, so we've got a variety of answers, but we've got, it seems like there's at least the most confident or the most number of people are saying C because I'm hearing it most predominantly. So someone that said C, can you tell me why you said C?
Because F over A will give you the highest answer.
Right, all of these, you kind of have a given acceleration, right? There's not a scale there, but a given acceleration. So as you increase the mass times acceleration would give you a greater force. So a greater force we would see as a steeper slope. So in this case, C would be our greatest mass because it has the steepest slope. So if we rank them from greatest to least, we would have C, A, B, D. So Charlie, Alpha, Bravo, Delta, C, A, B, D. Because we know that as we increase and add mass, that's going to increase the force, so the graph will go up, giving us a greater force at a given acceleration. Okay. All right, so we had our warm-ups. We're only 2 minutes behind, so we're doing awesome today. Let me ask you, how did the homework go? All right, let me ask you a different way. Do we
Mr.
want to
Wiley.
look at anything? Yeah, what's up?
Is the sum of forces also the net force?
Yes. Sum of forces is the net force, and the net force is also equal to mass times acceleration. So the sum of forces is equal to mass times acceleration, but the sum of forces is the net force, which is also equal to mass times acceleration.
All right.
It's kind of like 2 sides of the equation. They're equal to each other. On one side, you could just be balancing your forces. On the other side, you could be saying, well, what's mass times acceleration? And they're equal to each other. Because if your net force, if they're balanced, your net force is 0, right? Well, if they're balanced, you've got no acceleration. So if A is 0 times any mass, still 0.
I also have a question like the homework that we had over the weekend. I had a
Perfect.
question.
That's what we're going to talk about. What's your question?
Question 6.
Question 6. All right, let's take a look at it. Let's see.
I kind of knew how to do it, but all I did was 10 kg times 2.5. I got 25, and I added that to 50, and I got 75. And the thing is, I don't know how I got that answer though. I need a clear explanation.
That's perfectly fine. Let's take a look at this one step at a time. So yeah, you got a couple questions that may pop up in the middle of working the problem, but there's probably at least one person here that got to number 6 and was like, I don't get it. So let's take this number 6 together. It says a boy pushes horizontally on a 10-kilogram wagon and it accelerates at 2.5 meters per second. So the boy pushing on a wagon horizontally means he's applying a force. So I'm going to use that box on the left side to draw my free body diagram. And I'm going to say, okay, he's doing a force applied. So I have a force applied going, I'm going to say going to the right. Generically, when I have someone moving something, I have them moving it to the right. So it just makes things consistent. Now he's pushing a wagon. So I'm guessing the wagon is on the ground on Earth. Okay, there's some assumptions we can make. So we can say, okay, well, it's going to have a force of gravity. And since it's on the ground, it's going to have a force normal. And the force of gravity and force normal in this case should be balanced because it's not accelerating into the sky. It's not accelerating into the ground. So as far as the vertical is concerned, not the horizontal, the vertical, those 2 things should be balanced because it's a constant 0 velocity in the vertical. The vertical is the y direction. So I can go ahead and fill in this box and say, well, this would be force normal minus force of gravity. And that's going to be equal to 0, but I'm just going to leave it as the variables because I want to get used to variables. I want to be comfortable with the variables. I'm going to write down the things that they told me. They said that the mass equals 10 kilograms. it told me that the acceleration was, in this case, to the right, equal to 2.5 meters per second squared. And the reason I said to the right is because that's how I drew it. He's pushing it to the right, so it's accelerating to the right. I chose the right direction. You could have put left, so don't get hung up on that. It tells me that the frictional force is a total of 50 newtons. Now, on the first day of forces, we talked about contact forces and we talked about field forces, or like gravity and magnetism and all that. And we said that frictional force opposes movement. So if it's moving to the right and I have a frictional force, that force must be to the left because friction opposes movement. So I'm going to draw an arrow to the left and I'm going to say force of friction. And usually for friction, it's kind of a scripty looking F. So I have my capital F for force, and then I do a little scripty F for friction. And I made it a smaller arrow because we know it's accelerating to the right. So therefore the force applied is bigger than the force of friction. And that's what allows it to have an acceleration, by having that imbalance of forces. Okay. Now it said that it was a total of 50. So let me write that down. It says the force of friction equals 50 newtons. Okay. What is the magnitude of the force he is exerting? So we're looking for FA, right? And we know that our formula from Newton's second law is going to be the sum of forces is equal to mass times acceleration. Okay. And I'm going to break apart the sum of forces because I know how to add up the sum of forces. And what that's going to look like is the sum of forces is simply the force applied minus the force of friction, because the direction that we're accelerating in minus anything that's opposing us. Okay. Force applied minus the force of friction. And that is still equal to the mass times the acceleration. We're not changing that part of the equation. Now we want to solve for the force applied. So we need to add the force of friction over. So we're going to add force of friction over because we want to solve for the one. So plus force of friction. And we would have force applied is equal to, I'm going to put this in parentheses to keep it together, mass times acceleration plus the force of friction. So if we were only using variables, we can stop here because this is how we would solve for it. But since we have numbers, let's plug in some numbers. So the mass it told us was 10 times 2.5 plus, let me put these in parentheses, it just helps keep it together, plus the force of friction, which they said was 50. And then if we just, I'm going to continue this along the bottom just to give myself some room. 10 times 2.5 would give me 25 plus 50. So my force applied should equal 75 newtons. Let me just check my work. Yes, okay. I want to make sure I'm not making a mistake under the pressure of having 30-something people stare at me, right? So my force applied is 75 newtons, and that's the same answer that the worksheet got. So we should be in pretty good shape. If the wagon starts from rest, okay, now we sound like kinematics. So don't forget your kinematics, especially during retest time, right? Don't forget your kinematics. So it's saying we're starting from rest. So V naught equals 0 meters per second. How far will it travel in 7 seconds? So my time equals 7 seconds. They told us that the acceleration equals 2.5 meters per second square. And it wants to know how far will it travel? Well, that is simply a delta x equals question mark. And then the final velocity was never ever mentioned in all of this. We have an equation that does not have any final velocity as a part of its variables. And so if we look to our kinematics equations and we find that equation, what we should find, I think, well, let me cheat and look. Yep, it is. Delta x is equal to V naught t plus 1/2 at squared. All right, well, V naught is 0. 0 times anything, still 0. So we can take this part out, say that delta x is equal to 1/2 at squared. Okay, we're looking for delta x, so we can say this is 1/2 times 2.5 times 7 squared. So then delta x equals, I'm going to use my calculator, I'm going to type it all in together, So I've got 7 squared times 2.5 times 0.5, and that gives me 61.25. 61.25 meters, which is the same thing that they got. So this is how I would work it. What we're learning here is based on the sum of forces is equal to mass times acceleration. The net sum of forces is adding up the forces. Everything goes in one direction, and we're subtracting everything that opposes it in the opposite direction. We do not care about perpendicular forces. Those are handled separately. We look at the vertical, then we look at the horizontal. So if we looked in the horizontal here, in our box, we would have our force applied minus the force of friction. Sorry, I got to mark somebody coming in. And once I click admit, let me know. Any other questions about number 6? And let's see, we have just a couple of minutes to hit on some things. This was a very good example. I'm glad this one was brought up because this was a great example of how to work these problems. I don't have enough time to work a full problem, but I can hit on some topics and some concepts through this worksheet if there's anything else that we want to do here.
Mr. Watt.
Mr. Watt.
Ladies
ahead.
first. Yeah,
Okay.
ladies first.
All right. So some of the questions when they asked, like if they have a 10 Newton weight hanging from a string or a pulley,
Okay.
there would only be like, would there be 10 Newtons of normal force since it's staying in the same place or no?
Okay, good question. So you've got a 10 Newton, actually let me do this to where I'm not staring at like all this work. So I'm gonna stop the share so I can feel like I'm staring at everybody. Now I can see more people. So if I have a 10 Newton object, if I say it's a 10 Newton object, that means that the weight of the object is 10 Newtons. And we know weight and force of gravity are the same thing. Could you repeat why force applied minus force of friction is equal to force? Don't let me forget to answer that question in the chat. All right, so if we have a 10 Newton object, this is like saying a 250-pound linebacker on the football team. We're saying their weight, and weight is force of gravity, okay? So if we have a 10 Newton object, that's the force of gravity down. If it's hanging from a string, there's no normal force here because in order for there to be normal force, we'd have to put it on the ground. It's not on the ground, it's hanging from a string. So the string then would provide tension going up. And we know that because if we cut the string, the object would fall. So the string must be pulling up on the object because without the string, object's going down. Now, if the object is just hovering, like it's just hanging from the sky, like I don't know if you can see in the corner of this classroom, there's those balls hanging from the sky, right? Whatever those poofy things are, right? They're hanging and they're not accelerating up or down. So the tension in their string is equal to the force of gravity pulling them down. Now, if they are 10 Newton objects, that means force of gravity is 10 Newtons down. The tension must also be 10 Newtons up. For it to move up, the tension must increase. For them to accelerate upwards, the tension must increase. For them to accelerate downward, the tension must decrease because you're not changing the force of gravity. Did that answer your question or did I just dance all around it?
You did.
Okay, perfect. Now, let me hit on the chat. It said, could you repeat why force applied minus force of friction is equal to force? I think what you mean is equal to net force. Because what the symbol, it said the sum of forces, that's the same thing as the net force. If you get a job, not that you have to get a job, but when you get a job, you get a paycheck and it has like your gross pay and your net pay. Your net pay is basically how much money you're getting after they take away all your taxes. Okay, well, your net force is what's all the forces going one way minus all the forces going the other way, whether it's horizontal or vertical, okay? So your sum of forces is your net force. And in the case of the object that was being pulled or the wagon being pulled by the student, we had force applied, which was pulling it to the right, minus the friction, which was trying to resist that movement. So that was a force going to the left. I hope that answered the chat question. Now there was a gentleman, I didn't see who it was, but there was a gentleman asking a question. Let me hit on that one and then let's move forward. What was that question?
I was going to talk about number 7 where it had something to do with with a elevator and like a cable with tension in it.
Okay, so let's look at this one. If you've got your work in front of you, everybody go to number 7. It says the mass of an elevator plus occupants is 752. So 752 is the mass. If we have the mass, we should automatically in our brain say, well, I know what force of gravity is, because force of gravity is going to be mass times 10, right? So that would be 7,520 newtons down for force of gravity. The tension in the cable supporting the elevator is 8,950. Okay, well, 8,950 is bigger than 7,520. So now we know there must be an acceleration upwards because the forces, there's more force up than down, right? I don't even know what the question's asking yet. I'm just saying, hey, as I read this, this is what's popping in my head, right? I'm digesting this as I go along. It says, what is the net force? Well, in this case, tension is bigger than gravity. So I'm going to say the net force is going to be based on tension up minus gravity down, right? So I would calculate it by 8,950 minus the force of gravity, which we get by taking the mass times 10. It says, what is the elevator's acceleration? Okay, well, the acceleration is net force minus, net force is equal to, oops, got somebody else coming in. Net force is equal to mass times acceleration. Well, if we know the net force from the previous question, from what we just solved, subtracting, we can set that equal to mass times acceleration, divide the mass over, which they told us, you're left with acceleration, and that's how much it's accelerating upwards. Let's see. All right, come on. Okay, now, if we have any other questions about this homework sheet, that's totally fine. Tutorials, emails, communicate with me, but get that sheet done. There's so much practice there, and there's so much variation within the problems. This is an excellent worksheet. It was so good that I actually redid the first 2 pages just to refresh my mind on these. Usually I just kind of grab the stuff I've already done, but this one I actually sat down yesterday and spent the time doing it. And if I'm willing to do it multiple times, I'm not taking the test in May. You guys should go through every one of these problems and make sure you understand it. And not just, oh, after the 3rd one, I understood it. There is challenges all through this, through that homework. So get it done. Get it done. Okay, let's see what's next on my agenda. We're going to do some, we're going to spend 15 minutes on practice problems with Newton's second law. Then we're going to spend 30 minutes on friction, and that will finish our day. So I got to switch gears to this other computer. I end up making a really big mess around me because I'm using someone's classroom right now. All right, so share application. Let's go back to this. I'm going to quickly delete my work because someone else asked me about this in second period, and I want them the benefit of seeing it worked and not just seeing the work. And then let's go to this. Okay, so this is linked in Canvas today. It's there. We're going to work through this at least until the 40 minute mark. Ooh, we won't get past 9:45 on this. So between 9:40 and 9:45, we'll work through this as much as we can. Then we'll call it quits as a team, and then you'll be responsible for the remainder. This one's not that bad, so we should be able to do some of this. Be prepared to unmute so that we can talk through some of this together. I'll get us started, and let's just look at this. It says the velocity of a 1,000 kilogram car is shown. So this is a velocity graph, right? No mystery there. This is velocity over time. So we should be feeling like, hey, this is from like the first week of school. Graphs, I got this, right? Confidence. Then it says determine the acceleration of the car and the net force acting on the car. Okay, then our confidence says crap. Now it's asking questions. So how do I get the acceleration? This is where you got to unmute and talk to me. How am I going to get the acceleration here?
Slope.
Slope, absolutely right. The slope on this guy is going to be way easy too, because, oh, I got to fix this so it's not that. Okay, I can start at the origin, and then I can go up to this point. Those look pretty good points. Let me get the right color going. So if I'm looking at slope just in the easiest possible terms, we're looking at the rise divided by the run, right? The change in y divided by the change in x. So if we're going up to 30 and we're going over to, let's see, that's 5.5, 6.5. So that'd be like 30 divided by 6.5, right? Because the slope in this case is equal to 30 meters per second divided by 6.5 seconds. Too bad they didn't give us something that was easy to do. If I put that in my calculator, I get just about 4.62 meters per second squared. So that's where it comes from. And so then in the option A, if I get any of that math wrong, you got to tell me. I'm doing this for the first time for this year with you guys. So if I get something wrong, get the reward and say, hey, teacher, you're messing up. All right. And I don't mind. I actually enjoy finding errors. So 4.62 meters per second square. And the net force acting on the car. Okay, so for the net force acting on the car, we know that the sum of forces is equal to the mass times the acceleration, right? Okay, and we know that the mass, they told us the mass, didn't they? If I scroll this up a little bit, it's a 1,000 kilogram car. So we have 1,000 kilograms times the acceleration of 4.62 meters per second square. So then my sum of forces should equal 1, 2, 3. So 4,620 newtons. Does that seem fair? We know the sum of forces is mass times acceleration. They told us the mass. We just figured out the acceleration so we can put this together. So yes, if you've done the entire work, the homework coming into today, this should look pretty easy. If drag force acting on the car is 1,000 newtons, what force does the engine provide? Okay, this is where I want to create a free body diagram. Anytime we're doing something like this, it's always a good idea to create that free body diagram. So let me scroll it up. Off to the side, I'm going to create my free body diagram. And again, I like to say things move to the right. It's from playing Mario Brothers as a child, and the game only moved to the right. So there you go. All right, so I've got force applied going to the right, or actually this is a thrust because it's coming from the engine's car. So we have thrust, my engine, and then we have drag saying going to the right. So here I'm just going to write drag. Okay. Acting on the, so we've got my sum of forces is equal to, I know 46, and I know it's mass times acceleration, my generic force. I can also say that my sum of forces is equal to thrust minus drag, right? Because when I get my net force, that's equal to my sum of forces, and that's thrust minus drag. So let's write that over here. So my sum of forces is equal to net force. And that's what I've just done, thrust minus drag. Well, we've said that the sum of forces is equal to 4620, and they've told us that drag is 1,000. So if we wrote this out as an equation, we would say that thrust minus drag is equal to mass times acceleration, just to keep it all as variables. We're trying to solve for thrust, aren't we? What force does the engine provide? Yes, so we're going to add drag over. So add drag to both sides. And we would have thrust is equal to mass times acceleration plus drag. In the previous problem, we said that mass times acceleration is 4,620. 4,620 plus drag, they told us was 1,000. So thrust then would be equal to 5,620 newtons. I want to stop here and make sure you guys all catch up and ask any questions that you want to ask. We know that sum of forces is net force. We know that sum of forces is equal to mass times acceleration. Now we're putting it together. We're saying that the net force is thrust minus drag, and that's equal to mass times acceleration. We're rearranging it so we can solve for thrust. So since it's thrust minus drag, we're going to add drag to both sides. And we get thrust is equal to mass times acceleration plus drag. If this was the AP exam, we'd be finished because we've solved for thrust. We've told you how to get it. But here we have numbers, and we want to finish with the numbers. So mass times acceleration from the previous problem, we calculated at 4,620 plus the drag that they gave us in letter B gives us 5,620 newtons. Are we okay? All right. Let's make sure we kind of write this down so when you get to the problems that we don't get to, you're comfortable with this and you can move through it. Okay, let me take a quick glance and see. I think what we want to do, let's do this. Let's just finish the front page on this one. Let's do number 2 together, make sure we're comfortable. That way we have plenty of time for friction because we need to talk about friction and we need to be comfortable with friction. So let's scroll this up. And again, we've got a hockey puck of mass. I'm going to circle this so I can see it quickly. So there's my mass, slides across the ice rink and slows to a stop. Okay, so I know my final velocity is 0. I can see that in the graph. The velocity versus time graph of the puck is shown below. Okay, perfect. We've got a graph. And then let's just go ahead and write the mass down here. So when I scroll it up, we'll be able to see it. 0.16 kilograms. All right, now when I scroll this up, it's okay if it gets out of the view. Calculate the acceleration of the puck. Well, it's cool they gave us some answers, but we need to make sure we get the answers too. Okay, so what we need to do is calculate the acceleration of the puck. Again, we want to look at the slope. So I'm going to look at 2 points on the line. My slope, in this case, would equal, if I'm going down 24, I would say negative 24 meters per second. And I'm going from 0 seconds to 3 seconds. I'm dividing that by 3 seconds. So then my slope should equal negative 8 meters per second square. Okay, if I'm making a mistake, you got to tell me, right? So if I've got the mass and I've got the acceleration, actually, I just answered that one. So that one's done. Okay, because that's there, right? Calculate, I can do the net force, right? Because the net force, let's see, net force is equal to the sum of forces, which is equal to the mass times the acceleration, right? And they told us the mass is 0.16 kilograms times the acceleration we just said was negative 8 meters per second squared. And if I put that in my calculator just to confirm, I take 0.16 times 8. I get 1.8, but it's 1.28, but it's negative. So negative 1.28 newtons. And that negative is our direction. Remember, force is a vector, and we have to have a direction. But negative is a direction. It's going in a negative direction. So we finished the front page. We're right at the time mark. That was the ideal time to finish talking about this together. If there's any questions about what we've done, ask those questions. But I want you to finish this work between now and next class. If you get stuck on anything, let me know. Let's see, today's Tuesday, so we meet again on Thursday. Maybe by Thursday, I'll post the key. So if you get stuck, you'll have something to refer back to. But I don't want you to just using the key as a copy. This isn't like notes in history, right? You need to work it and then use the key to confirm your work. You need to getting through the struggle on your own means you're going to learn it. Looking at the key and just writing those things down, you're not going to learn it. I guarantee you that it'll be a huge difference when you're taking the test and you don't have a key sitting there. It's going to be tough. All right. Any questions about this before I move on? Can y'all still hear me? Because am I just talking to a screen? Okay. I'm getting some responses. Awesome. All right. So let me stop the share on this one. And let's take a breath. Let's see what's in the chat because I might have missed something. Okay, I answered that one. Is there a certain way we know which direction objects are moving? Yes, so is there a certain way we know which way objects are moving? That's a great question. Sometimes no, you don't know which way. Now, the Newton's second law will tell you which direction is the acceleration, but if you're in your car and you're moving in a positive direction and you apply the brakes, that is a negative acceleration. So you know the acceleration is negative, but if I didn't tell you the initial velocity, you don't know which direction you're moving. So Newton's second law does not dictate the motion of the object, just the direction of the acceleration. So that's actually a really good question. So I actually went to my new class instead of this one, but my counselor told me you have to stay in the class. Okay, yeah, no problem. Yes, schedule changes take effect, I think either Friday or Monday. So let's see if this, tell me wrong. Yeah, so Monday. So even if you're dropping, you still have to, for attendance, you still have to show up. And if you're dropping, still take the retest because you want as good of a grade as you can moving over. So, and if that's a concern, communicate with me. Let's talk about it. That's a good time to mention also, the drop date is good through Thursday. I sent everybody that's an IHS student, I sent you all the same email over the weekend. Everybody got the same message. I warned you I was going to. And the reason I said just IHS students, because the link was only good for IHS. I know I have a couple of students in this class that are from other campuses, so I'm sorry you can't be a part of our cool campus, but at least you get to be in our cool class. But if you need the link for your campus, let me know. I'll reach out to the counselors at your school and find that link. But I did just flat send it to all the IHS students, so that way you could go through and look at your grades like I recommended. If you're not where you need to be, can you make those adjustments? It is vastly important for you to make that decision. And if the decision is stay, great, but you got to do the work. Otherwise, would you rather be in an on-level and passing or an AP and failing for the student that has to make that decision? Do the work, do the work. All right, I think that's everything that's in there. So now let's talk about friction. Let me move my notes around. All right, we know a little bit about friction so far. We've talked about it even today. And share. All right, so let's switch over to the grid. This is my note paper, I guess. So if we're going to talk about friction, let's define what friction is, okay? Or at least a formula for friction. So friction, the force, I need writing tool. I need it to be skinnier and black. All right, now let's false start, try again. The force of friction is equal to the coefficient of friction times force normal. Okay, now what does that mean? Well, there's an easy way to remember that. If we look at FUN and say that friction is fun. So you'll never forget what friction is now, because I just told you friction is fun, which means friction is equal to the coefficient of friction times the normal force. So let's define these real quick. So this mu, this Greek letter mu, it looks like a U with a tail on it. That is a coefficient of friction, coefficient of friction. All right, and then we know that Fn is force normal. So if it has force normal as a part of its equation, that should tell us that friction is a contact force. Without contact, you got no friction, because without contact, you've got no force normal. So let's write that down. Friction is a contact force and is directly related to the normal force. All right, so we get normal force, but what about that coefficient of friction? The coefficient is a known value. You can think of it as a constant, sort of. It depends on the two surfaces that are rubbing together. So if we took two things that are slick, so two polished surfaces, and we put those together and we cause one of them to rub across the other, their coefficient of friction would be very small because they're slick. If we took two pieces of wood and wrapped them in sandpaper and try to scrape them past each other, the coefficient of friction would be very high because they're going to have a lot of friction. They're going to kind of oppose that sliding motion, right? Now, if you have two surfaces, you can look it up in a table and it'll tell you what the coefficient of friction is. You can Google it and say, hey, two pieces of wood, what's the coefficient of friction? Now, yes, there could be some variance because how the wood is sanded and the type of wood it is and which way is the grain going, yes. But the idea is the coefficient of friction is usually a known value. And it varies depending on what the two surfaces are, okay? So kind of wrap our minds around it. The coefficient of friction we could get from a table, okay? We could calculate it based on experimental circumstance, but it's based on the two surfaces that are rubbing together is your coefficient of friction. Now we know the normal force is going to be based on mass, because if we're not moving vertically, we know that the normal force is balanced with the force of gravity, right? And the bigger the mass, the bigger the force of gravity, bigger force of gravity, bigger force normal. So we can kind of get all of that. Let's see, I had something pop up in the chat. Let me scroll so I can see it. What about the coefficient of friction on a puck on ice? If we say that the ice was just cleaned by the Zamboni because we've been watching the Dallas Stars and last night was not a good night to watch them because they lost the second game. But most of the time we're going to say that ice is frictionless. Most of the time we're going to say ice is frictionless. Now, is ice always frictionless? After the Zamboni it is, but right before, at the end of the period for hockey, or right before they clean the ice isn't frictionless because it starts to get layers and all this stuff. But for the most part, for most questions, we'll say ice is frictionless. Okay, let's get through the notes just a little bit. I have a couple more things I want to write down. I want to get into the practice problems just a little bit and then talk about what we want to do between now and next class. So let me scroll this up. We've had enough time to see it. So if we were to draw something, we can say, okay, this is my surface, the little line. So this is my table surface. And then if I draw an object, I've got this free body diagram sitting there. We know that downward would be the force of gravity. We know that upwards is the force of normal. Our force applied would be to the right, so my force applied. And then my force of friction would oppose the force applied. So this would be my force of friction. That's pretty straightforward, okay? I haven't blown anybody's mind with that one because we know force of friction from our homework coming into today opposes motion, right? So we can go through this and say, well, the force of friction is equal to mu times force normal. And then the force of friction, in this case, we can say that we have a sum of forces. So our sum of forces in the horizontal, or in the vertical, let's say the sum of forces in the vertical is the force normal minus the force of gravity, okay? That's our vertical forces in this case. And my object, it's not accelerating off the ground. It's not a rocket ship. It's not accelerating into the ground as if it's, or it's not going into the sky like a rocket. It's not going into the ground like quicksand, right? It's just chill on the ground as far as the vertical is concerned. So that means that the force of gravity, I can say that my net force is then 0 if it's not accelerating vertically, right? So my force normal minus my force of gravity, those are balanced forces in this case. So if I add my force of gravity over, I could say the force of gravity is equal to the force normal, right? Those are balanced in this case. If I say that, couldn't I then say that my force of friction is equal to mu times the force of gravity, if they're equal? I'm just taking my original equation and I'm bringing it down here based on that. Based on force of gravity and force normal being equal to each other, I could say that the force of friction is mu times the force of gravity. Only when they're equal, only when there's no acceleration in the vertical for this instance. Okay, so we've got that. Now, what if though the surface is a wall? So this is my wall. Okay, here's my object sitting against the wall. This is like me taking my calculator and I'm pressing it to the wall. So if you can still see my video image, you can see I'm pressing my calculator to the wall. I'm applying a force towards the wall, right? So if we go to our picture, my force applied goes this way, force applied. Okay, now my force of gravity is still down. We can test that, not with my calculator, we're not. But we could test that. You drop something, gravity's still going down. All right, force of gravity down. Which way is my force normal going? I want you to unmute and use words. Which way is my force normal moving at this point?
To the left.
To the left, absolutely right. And it's going to the left because it's perpendicular to the surface. Okay, perfect. So my force normal is going to the left. What about my force of friction? Which way should I point it?
Upwards.
Upwards.
Why upwards? Not just because it's the one direction I haven't gone yet.
Because it's moving downwards, right?
Right. The only direction my calculator is going to move at this point is going to be downwards, right? And force of friction opposes movement. So my force of friction in this case would be upwards. Now, if it's balanced, if I balance those arrows up and down, that means it's not moving. According to the way I drew it now, the force of gravity is greater than the force of friction, so it would be moving down the wall according to how I just drew it. If I wanted to indicate that it had a no acceleration, I would need to draw it maybe that long, something like that, so that they have the same magnitude and length of the arrows. I'm not going to get a ruler out, but it should be easy to tell. Okay. So for this one, let's see if I've got enough room to write. Yeah, I do. Sweet. All right. So I'm going to scroll that over just a bit so I can see, we know that the force of friction is equal to coefficient times force normal. That's been stated a couple of times, even on the sheet. And we know that the sum of forces in the x direction, normal and applied, in the x direction is equal to force normal minus force applied. That's supposed to be an n. Let me fix that one. That was just too nasty. Okay. In this case, that is, their forces are balanced because it's not moving into the wall, it's not moving off the wall. So their forces are balanced, that's equal. So here, the force normal minus the force applied, if I add the force applied over, I can say that the force applied is equal to the force normal. Fair enough? Okay. And then if I come down, I can say, what about my summation of forces in the y direction? Would be equal to the force of friction minus the force of gravity. If these are not moving, if this is also balanced, a net force is zero acceleration, equilibrium, all of those things are true, we can say that 0 is equal to the force of friction minus the force of gravity, and therefore the force of gravity is equal to the force of friction. We okay with this? We created we couldn't do these equations without the free body diagram. We've got to draw that free body diagram so that we can see what it is and then put it together in the equations, right? So this practice is very important. The last bit of notes I'm going to do for friction, I'm going to scroll this up just a bit, and I'm going to write down something that I want to make sure that it's clear, and that is friction always opposes motion. Friction always opposes motion. So what if we had something that was on an incline? All right, that's my little surface with the lines. Okay, and then this is my object. Okay, now the force normal, I'm going to draw these so that we can see it. And it's also hard to say verbally across the Zoom for you to guess what it is. But my force normal is going to go this way right here, right? Because it's perpendicular to the surface. So this is my force normal. Now my force gravity. With your hand, point to me, what is the force gravity going to look like? Absolutely right. Yes. Force of gravity still goes straight down. So we see in this example that force normal and force of gravity are not straight in line with each other. The force normal is perpendicular to the ground, but if the ground's at an angle, gravity doesn't care. Gravity still goes straight down. So if we're pushing this object up the incline, our force applied would be this way, and our force of friction would be down the incline. Okay, this should bring about one fear in your mind now. It's like, does that mean we're going to be doing sine and cosine on that force of gravity? And yes, we absolutely will be, but not today, right? So that, how far does that bring us into today? We want to get to this just a bit. So I'm gonna give you a second to make sure you have this written down. I'm gonna switch over to that last thing. We're gonna spend just like 5 minutes getting started on it because I don't want to talk for a whole hour, but it's gonna be really close. So if you've got this, if you don't worry. This class is gonna be posted on our Canvas page. I'm posting first periods now. So if you don't know, when you go into Canvas, you click on our class, there's that link for Zoom recordings. All of these are showing up. So you get to rerun this class as much as you need to. So let's switch over and look at this page. This is the last one that we're going to get started together. And then you guys are going to look at between now and next class. We actually have a lot to do between now and next class. So let's not waste time. We've got a 10 kilogram object is resting on a table. Okay. So if we've got an object, let's draw this object. Oh, that was not what I wanted. All right. So we need drawing. We want this. Okay. I think that's what we want, right? Yep. Okay. So we've got an object, 10 kilogram object. There's my object. It's resting on a table. That means that its forces are balanced, right? If it's resting, no acceleration. So we can say it's on a table. So we know we have a force normal. We're on Earth. So we have a force of gravity. Okay. It's resting on a table. So I know that my Fg is equal to my Fn. Okay. This is my mass. I'm just start writing all over stuff, right? The coefficient of static friction between the object and the surface is 0.6. The coefficient of kinetic friction between the object and the surface is 0.3. Wow, that just got a lot harder, didn't it? Now we've got two coefficients of friction. All right, let's think about it. You ever try to move something and you had to give it a lot of force to get it moving because it was kind of stuck? But once it started moving, it was kind of easy. All right, well, that's what's going on here. The coefficient of static friction is what gets an object moving. Once it's in motion, you remove the static friction coefficient and you put in the coefficient, you use the kinetic coefficient of friction. Let that digest for just a second. Okay, now we have to ask ourselves, is the object moving? If the object is not moving, we use the coefficient of static friction to determine the friction. Once the object is in motion, we use the coefficient of friction that is kinetic. So the friction is going to be higher when it's not moving. And then once it's in motion, friction is going to drop. Okay. And if you think about moving furniture, if you've ever had to move a couch in your living room and you're like, you push on it, doesn't want to move, and you give it a nice push hard and it starts moving, and now you can kind of move it around a little bit, but as soon as it stops, it's kind of hard to get going again. That's what we're seeing here. Okay. So then let's look at all of this stuff kind of together. So we've got a 10 kilogram object. So then the force of gravity, let me just kind of make some notes. So my force of gravity is going to be equal to mass times acceleration, which is 10 times 10. So my force of gravity is equal to 100 newtons, right? And my force of gravity is equal to my force normal. So they're both 100 newtons. Kind of get that out of the way, the easy stuff, right? Okay, what else do we need to know? If the applied force is 30 newtons, so we're going to apply a force applied. We're saying the force applied equals 30 newtons. Determine the frictional force and acceleration. Okay, so for static friction, I'll just use the little scripty F when I'm writing it out. Static friction would be equal to 0.6 times force normal, 100 newtons. Am I on your way? Okay, perfect. All right, so if we want to calculate force of friction for static, we would say that this would be equal to what, 100 times 6? What's that going to be, 60? Yeah, 60 newtons. All right, my static friction is 60 newtons. In order to move the object, I have to overcome 60 newtons of static friction. Now, our applied force is 30 newtons. Did we move that object? Absolutely not. Because the force of friction is 60. If we have an applied force of 30, we did not move this, so the acceleration is equal to 0. Okay. How does this feel? Because I'm about to add one layer of complexity. So I want to make sure we're comfortable here. It said the object was at rest. It told us then the static coefficient of friction was 0.6. So we calculated what the static friction is, right? And if we didn't overcome the static friction, it didn't move. For static friction, why would we use normal force? Because our formula is coefficient of friction times normal. Whether it's static or kinetic, it's still times normal. That doesn't change. Which coefficient you use is determined whether or not it's in motion, okay? But now this is one piece that's going to blow some people's minds. I'm sitting at a desk, okay? Actually, let me turn this and show this desk next to me, okay? That desk next to me, sitting right there, has a static of coefficient, it has static friction, right? I have to overcome the static friction to get it to move, right? So let's pretend that this problem was talking about that desk, okay? The static friction is going to match the force applied until I overcome it. What does that mean? Okay. What that means is if that object has a possible static friction of 60 newtons, if I push on it with 5 newtons, it will have a static friction of 5 newtons. If I push on it with 10 newtons, it will have a static friction of 10 newtons. Now, how does that make sense? Okay, well, if I just said that the static friction is a force opposing motion and I push on it with 5 newtons and the static friction was 60 newtons, wouldn't that mean that it would accelerate and crush right through my legs because of an imbalance of forces? Let's think about it, okay? Let me stop the share so I can see more people and you can see better too. Okay, let's think about it. An imbalance of forces means acceleration. Is that desk next to me accelerating right now? You got to respond. Is that desk accelerating next to me?
No.
It has 0 acceleration, but has a constant velocity of 0.
Correct. And that means the forces are balanced, right?
Yeah, correct.
Right. So if I push on it, the static force is going to match my applied force until I overcome the static force and then the static friction, and then static is going to drop down to kinetic and the object will be accelerating. What I want you to realize is that when you have kinetic friction, that's going to be a set value. It's in motion. The kinetic friction is 10 newtons. Okay, it's always 10. But for static, if we say that static can be 60 newtons or is 60 newtons, that just means static is somewhere between 60 and 0, from 0 to 60, and it's going to match the force applied until it's exceeded. It can't be just 60. If it was 60 and I'm trying to push it towards the window and I push on it with 10, I can't have a net force of 50 back at me because that means that desk is going to cut right through my legs and sail right into the wall behind me. That would be weird, right? So what it means is that static friction is going to match the force applied until it's overcome. And it's overcome at its value that you calculate. So if you say, okay, static friction is 60, that means that it's going to match the force applied until the force applied exceeds 60. And at that point, you recalculate friction based on kinetic. All right. How confusing is that?
So, Mr.
So-
Wiley, are you implying that static friction is the same as the force applied?
Until force applied overcomes it, yes.
All right.
If I'm not pushing on the desk has no static friction. And the static friction will match my force applied until I overcome it.
Is static friction still present if the object is not even at motion? Like say it's at 0 meters per second, like it's not moving at all, it's in rest. Is static friction still present in that scenario?
As long as there's a force applied, yes. As long as there is a force trying to move the object, static friction is present. If there is no force trying to move the object, static friction is at 0
All right.
because it has to be balanced.
Mr. Watley,
Yes.
so I had a question. So you said what do you say? You said that static friction only exists until you exceed it. So let's say I was at 61 newtons. Would my kinetic friction be would my kinetic friction still be 60?
No, because you're going to use a different coefficient of friction. Once it's in motion, once you've overcome the 60 newtons, and let's say you're pushing at 61 newtons, and you say, oh, I have an acceleration now because I have an imbalance of forces. Your friction is no longer static because it's in motion. So then you need to throw away your static friction coefficient and switch to the kinetic friction coefficient. Let's look and see if this worksheet goes into that. I don't remember how far it goes, but I wanted to stop and discuss that. So let's see. All right, in problem 2, it says if the applied force, or B, it says if the applied force is 58.8, determine the frictional force and acceleration. Okay. Since the static friction peaks at 60, if I apply 58.8, what's the static friction?
58.8.
58.8. So my friction, my force of friction would equal 58.8, and I've got no acceleration. Because if I said, no, the frictional force is 60 and the applied force is 58.8, that's an imbalance of forces, and that would indicate an acceleration. That's why static force is one of those things, as soon as you wrap your mind around it, it's easy. But when you first hear about it, you're like, wait, it changes? Absolutely changes. It's going to resist movement and only do, it's like a freshman, okay? They only do what they have to do. Static friction only does what it has to do, okay? So let's think of it that way. Now, if the applied force is 60 newtons, determine the frictional force and the acceleration. As soon as we match it, it's in motion, okay? And I think on this worksheet, it's assuming that our frictional force is 58.8 because that's using gravity at 9.8. So let's change this number and say, what if this said 70 newtons? If the applied force is 70 newtons, what would happen? Are we going to be in motion? Okay, because we've overcome static, we've exceeded that 60, because we have to go over 60 by at least a tiny bit, right? If we're exactly the same, we're still balanced. So let's say the problem said 70 here. So 70, it exceeds our static friction. So now our friction is going to be kinetic. And we need to scroll back up and see what the coefficient of kinetic is. We see that it was 0.3. So our force of friction is going to be equal to 0.3 times the force normal. And we said the force normal was 100. So that equals 30 newtons, right? So then our sum of forces would equal 70 minus 30, because 70 applied, 30 opposing. So our sum of forces would equal 40 newtons, right? So we've got our frictional force is here. That answers that question. And then we want to know what the acceleration is. So the sum of forces is equal to mass times acceleration. If we divide mass on both sides, they cancel on the right. So our sum of forces we said was 40. So 40 newtons divided by the mass, I got to peek at what the mass was. 10? Yeah, 10. Divided by 10 kilograms equals the acceleration. So our acceleration in this case would be 4 meters per second square is the acceleration. As soon as you overcome static, then force of friction for kinetic comes in, and that's constant. It's just like every other force. It's not changing. It's not messing with us like the other one did. But we just need to remember.
Mr. Watt, sorry.
Yeah, what's up? Go
So
for
you're
it.
saying from force 0 to whatever the static friction is, like the friction, what do you say? There's no movement, but after you exceed that static friction, the value is now like there's a new value which is the I
Kinetic.
forgot what it's called.
Kinetic.
The other type of friction. The
Yeah, kinetic friction.
yeah,
So your
yeah.
coefficient of friction for kinetic is going to be less than static. So if it's 60, it was 60, right? Once we overcame 60, friction drops. Well, our applied force is still high and our friction is low, so you have an imbalance of forces, you're gonna have an acceleration. And the only way you would then get a constant velocity would be to reduce. So at this point, you have an acceleration of 4 meters per second square. And then if you wanted to not keep accelerating, you would just need to reduce the force applied to match the friction, and then you would just maintain a constant velocity. Let's see, another question popped up. So once the applied force exceeds the static frictional force, you then use the kinetic frictional force. Actually, absolutely correct. Absolutely correct. So we use static friction when the force applied is less than static friction. You use static friction when you're not in motion. Okay, so don't confuse this, because what if you're pushing something and now you start pushing at a force less than the frictional force? It'll start to slow down. You'll have a negative acceleration. But just because your force drops below that of friction doesn't mean you switch to static. Static means you're not moving. If you're in motion, you're using kinetic. If you're not in motion, if you are not moving, your velocity is 0, that's when you use static.
Mr. Watley,
Yes, what's up?
so when you break even between the applied force and the static force, are you still,
Exactly break even?
what happened?
Are you saying when they're exactly equal
Right,
to each other?
Yeah, if they're equal to each other. I know you said that it's technically in motion now, but when
Well, I was saying is you've got to exceed it by just a little bit. Okay.
Mhm.
So if it's 60 and 60, I don't think we're going to see it exactly equal, but you're going to have to be like, if your static is 60 newtons and your applied force is 60.00001, you've broken it. So
Gotcha.
you have to exceed it by the smallest amount.
Thank you.
Okay.
Wait, and the coefficient's different every time?
The coefficient of friction is based on the two objects. So like 2 pieces of wood would have the same coefficient of
Okay.
friction, but if you take a piece of wood off and put a piece of rubber down, it's going to be different. So the coefficient of friction is based on the 2 surfaces that are in contact together.
All right.
Just like with anything else, in order to solve for the coefficient of friction, if you had to, you're going to have to know the force normal, and you're going to have to be able to calculate the force of friction and then determine coefficient of friction. So you'll always have enough pieces with one thing missing. As we go into the sheet, you can see that the next problem, like it's giving you acceleration and mass. So then you just start plugging things in. Oh, the coefficient of friction is also there. So this is going to be one of those things you just kind of build it as you go. From 2 and 3 on, they give you free body diagrams, and then it's like a puzzle. Based on what you have, what can you fill in? Now that you fill that in, what can your next step be? All right, let me do one last thing. We've started 2 worksheets together, or 2 packets or whatever together. You've got to work on those between now and next class, but also one last thing is this is a really simple thing, at least it's short. I also want you to look at this inquiry lab. So it says homework for next class, inquiry lab. This one is talking about friction, and it's talking about how could you set up an experiment in order to calculate these things. So you've got to think through this and take everything that you know and decide what could you do to calculate this in a lab environment. So I want you to finish the sheets that we started, which are let's see, yeah, you can see my mouse. The practice problems, this one, and friction with notes. These 2 bullet points, I want you to work through really well. And then I also want you to do the inquiry lab as best you can between now and next class. So those 3 things, and yes, today's Tuesday and next class is on Thursday. So make sure that you can keep up with this work, and it's a great time to, the drop date is now. So if you can keep up, do this work. If it's too much, you have your exit strategy right in front of you. If you have questions, concerns, make sure you're emailing me, and you're also showing up to tutorials. I think I had 3 people this morning Yesterday afternoon, I had 5 people, and this is across all 3 teachers. That was the volume of people that felt like they needed assistance. So if you're not coming into tutorials, you must understand it all, and you must be doing the work, right? Right. Okay, let's see. I'm going to stop this. If we try to do the lab and don't have all the necessary materials, can we substitute materials in them? I think in that lab, it says you're going to say what you need, but it has to be based on things that you could normally find in a high school lab.